All right, let's go ahead and continue. We're now on problem number 30. And what we're going to do is we're going to complete the form here. We're going to begin with the molecule CH4. So the name of this particular one, if we're going to use the IUPAC names, this is going to be, it's got a common name, but the non-polar or the covalent name is going to be carbon tetrahydride is the name if we're going to use that way. Otherwise, the name here would be methane. And so let's go ahead and put those names up top here. So we can call this methane. That's the common name. Or we could say carbon. And then we would put here tetrahydride. The Lewis dot structure for methane here is going to be a carbon is the center atom. So if we look at the Lewis dot, we got to go and count valence electrons. So carbon is going to have 4 valence electrons here. So when we do that, that's 4. Each of the hydrogens has 1, and there's 4 of them. And if we take the total count here, that'll give us a total of 8 valence electrons. So which means when we come in here and do the Lewis dot structure, we are going to get the carbon in the center. There's a hydrogen up top, 1 to the left, down, and to the right. Then the rule says give the atoms here that have the higher electronegativity, in this case the hydrogen, give them the octet. Hydrogen can only fit 2 electrons. So we've got 1, 2. There's a bond going to be formed there. And so we'll do that there. We'll do the next one. There's 1, 2, 1, 2, and then 1, 2. That'll give us a total of 8. So that's 2, 4, 6, 8. We only had 8. There are no remaining electrons. They're all going to be shared with the carbon at each bond. And so this would be the Lewis dot structure for methane. The molecular geometry, because we've got 1, 2, 3, 4 of these atoms bonded to a central atom, this particular structure is going to be tetrahedral. Going on to the next one, we've got CO2, 1 carbon, 2 oxygens. This is a covalent compound, so let's begin with the name. This is going to be carbon, and the 2 is di, and then oxygen is oxide. If we look at the number of electrons here, valence carbon again is going to have 4, oxygen has 6, but there are 2 of them, so that gives us a total of 12, plus the 4 gives us a total of 16 valence electrons. So what we'll need to do here is put the carbon in the center, and then we've got an oxygen to the left, oxygen to the right, and what we're going to do here is we are going to go ahead and put the electrons at each of the positions for the more electronegative atom. That actually in this case is going to be the 2 oxygen atoms on either end. So what we'll do here is we will give the oxygen its octet. 1, 2, 3, 4, 5, 6, 7, and 8. There's a bond there. And then we'll do the same thing for the other oxygen. Now this is going to wind up being a problem for us, largely because the oxygen over here has 8 electrons, 2, 4, 6, and 8. And the other oxygen has an 8. But when we start looking at the electrons for carbon, carbon only has 1, 2, 3, 4. So that means it does not have enough. So what we will need to do is take some of the electrons from here, bring them down to form a double bond. And so let's go ahead and do that. Let's go ahead and erase. Sorry about that. Let me go ahead and erase this. I'm going to take these electrons away, and I'm going to share them right here in the center. So let's just put them above, and there's the bond. We can do the same thing for the other one. And so let's take these electrons away and put them in the center. And so that's what I'll do here, there and there. Now, when we look at the electrons, we've got 2. Let me change colors here so it's a lot easier to see. You've got 2, 4, 6, 8 for the oxygen, 2, 4, 6, 8 for the carbon, 8 for the other oxygen. So here's the Lewis dot structure for carbon dioxide. Notice that there are no lone pairs in the center atom. Even though we do have double bonds, there is no lone pair above or below. And so the structure here is going to be a linear structure. And so that's what we will put here. Linear molecular geometry. All right, so the next example here is H2O. Now the common name for this compound is water, but we want to use the naming convention. So that means that we've got 2 hydrogen, so that is hydrogen, and there's only 1 oxygen, so that would be monoxide. So the formula here for this particular compound is going to be dihydrogen monoxide. The common name is water, though. So let's go ahead and do electrons. For the electrons here, that is 2 for the hydrogen. For the oxygen, that's 6. So that means that gives us a total of 8 electrons to use for the Lewis dot structure. So let's go ahead and get that done. The oxygen is going to be the center atom. So we've got an oxygen atom with a hydrogen to the left, hydrogen to the right. And even though the oxygen is the more electronegative atom here, what's going to happen is we're going to give the electrons to fill up the atoms here first, above and below. We're going to form bonds between the oxygen and the hydrogen. So what we'll do here is we're going to go and put 1, 2, 1, 2, and then we'll form a bond left, and then we'll form a bond right. So I know I drew the right one first, but here we go. We do have an octet on the oxygen. We do have an octet on each of the hydrogens. But notice here at the very bottom and at the very top, we've got a lone pair. If I draw those kind of the way I did in class, there is your lone pair. And because of the lone pair, what's going to end up happening is that these lone pairs will push down on this bond. Even though it's flat on the screen the way I've drawn it, it's actually going to give us a bent shape so that the 2 lone pairs are actually going upwards. And so it'll be a similar structure to the following. Let me just quickly sketch it. You'll get your lone pairs up top, but the hydrogen atoms will come back down. And then you get 1 lone pair in each of these directions. And so it's these lone pairs that are going to push the hydrogens down, and that's why you have a bent structure overall. And so that's what we've got here. So this is going to be bent molecular structure. Finally, the F2, this is fluorine gas because it is 2 of them together. This one here is not going to have any name other than it is a gas. It's a diatomic. You could say difluoride, but this is a fluorine gas. Because of that. And so each of these atoms is going to have its respective number of valence electrons. Fluorine, if you look it up on the periodic table, it's going to have the following number. It's going to have 7. And so when we come in here, let's go ahead and change the color. Let's change it to purple after we do this. So it's 7, but there's 2 of them, so that gives us a total of 14. Since it's the same atom, we're going to get 1 fluorine to the left. Let me take the bond off. And we've got a fluorine to the right. We'll give each atom a complement of electrons here. We've got a total of 14 electrons. So that means that we'll have an octet. We're going to have some sharing going on here between them. So that'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So the bond that forms between them is a single bond. And so if you do that and you count the electrons, you've got 2, 4, 6, 8, octet to the right, octet to the left. Since this isn't a line, the structure here on this one here is going to be linear on that one. Let's keep going here. Number 31. What is the molar mass of Fe2O3? Well, the way I showed you in class was, let me zoom in a bit. So the way I showed you was to take this and break it apart. If it's easier for you just to do the math on your calculator, then do that. But what I want to show you here is kind of what I've been showing you all along. We want to make sure that we count or identify the different atoms. So we've got 2 atoms. We've got an iron, and then we've got oxygen. Then we're going to count how many. So here we've got 2 iron, and we're going to represent that in the parentheses. And we also have 3 oxygen. So we're going to put that down here in parentheses. Oops. Then what we're going to do is we're going to place an equal sign, and then we're going to do the following. We're going to replace the symbol for each of these. We're going to replace it with the actual mass. So if you look at the periodic table, you'll get that mass. Let me bring one up here on the screen. So the iron is here. The mass is 55.845. So let's go ahead and move that aside and then write that down. So here the mass is 55.845. And if we look for oxygen, let's bring that on the screen so you can see it. Oxygen's molar mass is going to be 15.9994. And so we'll bring that down here as well. Let's just move this over. And so this is going to be 15.9994. Now, keep in mind that this value here, it's based on the periodic table that I'm using on this video. You want to make sure that you use the periodic table masses that are provided to you, or the masses that are on the packet that you use in your respective class. So what we've got here is we've got the masses now, and we're going to go ahead and multiply by 2 in the top, multiply by 3, and then we're going to equal this mass over here at the far end. So go ahead and do that off screen. I'm just going to put the masses totals here for you, and then come on back. So I've already gone ahead and done that for us. So if we take this number here, 55 times 2, all the way through being accurate, we'll get 111.69. And if we take the mass of oxygen times 3, we'll get 47.999. Now, what do we do next? The next thing we're going to do is we're going to take these numbers here, and we're going to add them up. And the total that we're going to get here is 159.6882. Now, how much should you report as a final answer? Well, since there was no number given to us in the problem, we want to go ahead and report what we want to report, I guess, here. There is no significant figure given. And so typically what you want to do is give a little, at least 3. And so I could put 159 as my number. But remember here, the 6 is greater than 5, so I could report 160. If you're not sure, maybe just the 3 and maybe a digit afterwards, since there was no real significant number provided in the original problem. So we're not entirely sure how many to report, but whenever in doubt, like in this particular case, you want to go ahead and report at least 3. So if that's the case, we'll report the 1, the 5, and the 9. We'll draw a line. The 6 is greater than 5, so that means that this 9 becomes a 10. So the final answer that we're going to report here should be 160 grams per mole of that particular compound of Fe2O3. And so there is your answer. All right, let's go on to problem number 32. How many molecules are there in 48.0 grams of O2? Now, since we're providing a number, let's go ahead and figure out whether we're going to report 3 or more significant figures here. So if we look at the numbers here, the 4 is significant, the 8 is significant, and the 0 is significant because of the decimal. So we're going to report 3 sig figs in our final answer. We are looking for molecules. That's the unknown. So look at the word how many. So that's how many, and we're looking for molecules, and we are starting with grams. So our starting amount is 48.0 grams of oxygen. And we want to know how many molecules. So we first need to convert into moles. So we're going to go ahead and take this. Let me go ahead to do it this way. We're going to multiply by a conversion factor. So the conversion factor that goes here is 1 mole of oxygen has a mass of 32 grams of oxygen. So that's just the molar mass of oxygen. And then we're going to multiply this by Avogadro's number. And Avogadro's number says that for every 1 mole of oxygen, it's going to have a specific amount of atoms. So it's 6.022 times 10 to the 23rd. And in this particular case, atoms or molecules, it would be the same thing, of O2. And so here what we'll do is we'll cancel the units that can cancel all the way across. And notice we're going to be left with molecules of oxygen, which is exactly what we're after. So what we're going to do is we are going to multiply the 48 times the 1 times the 6.022 times 10 to the 23rd. That'll give us a number in the numerator. So let me go ahead and do that, and then I'm going to divide it by 1 times 32 times 1, so 32 in the denominator. So I'll set it up show you on the screen in a sec. So here's the number that we're setting it up. I'm going to go ahead and plug this number into the calculator, and the result should be my answer. So my answer here, if I go ahead and do this, I'll just put an equal sign. That answer should be 9.033 times 10 to the 23rd molecules of O2. Now remember, we had established that there was only going to be 3 sig figs, so now we've got 4 sig figs in the coefficient, which means we're going to have to make a decision here. The 9 counts, the 3 counts, the 0 counts because it's between the 9 and the 3, but we don't need to report the final 3, so we can drop it because actually it is lower than 5. So we can drop it, so our final answer here should be 9.03 times 10 to the 23rd. And this is going to be molecules of O2. So here is your final answer for that particular problem. All right, so for this problem, what we've got is we're trying to figure out the moles. So here's my question mark. How many moles I've got? That's the unit I'm after. Here's my starting amount, and I've got the unit of grams. I do need to figure out what the molar mass of this compound is, so let's go ahead and do that really quick here. You can do that off camera. Essentially what I'm going to do is I'm going to take the mass of 3 oxygens, the mass of 1 nitrogen, the mass of 1 potassium. So if I write those numbers down here, this is 39 for the potassium. Add that to 14, which is the mass of the nitrogen, and then I'm going to add that to 16 times 3 because there are 3 oxygens. And if I add all of that up, the following is the molar mass. All right, so there it is, 101. I am using whole numbers. You want to be accurate. If the problem is asking you for accuracy, you definitely want to be accurate. But for the simplicity, I'm going to go ahead and use whole numbers. Since we are looking for how many moles, I'm going to start with the starting amount here, and I'm going to go ahead and write down 25.3 grams of KNO3. Take that, I'm going to multiply it by the molar mass, and so 1 mole of KNO3 is going to have a mass of 101 grams of KNO3. That allows me then to come in here and cancel the grams of KNO3, leaving me the number of moles, which is what I'm after. On the far right, I'm going to wind up getting here 25.3 moles of KNO3. I'm going to divide all of that by 101. The final answer at the bottom here is going to be the following. So here is the final answer, 0.250 moles of KNO3. All right, and for the final problem, number 34, we're going to look for the percent by mass of potassium in this compound. So here's the deal. The simple way to do this, since we're only being asked to find the percent of potassium, we're going to take the mass of potassium, so that will be the molar mass of only the element potassium, and then we're going to divide it by the molar mass of this entire thing. So if we do the molar mass, let's just figure that out really quick. And so the molar mass is going to be the following. So the mass of potassium, we know it's going to be 39 grams, so that's important. The mass of hydrogen is 1. The mass of carbon is 12. The mass of oxygen is 16. There's 3 of them. And if we add all of these together, that'll give us the molar mass. So that number here is molar mass. But this is molar mass of the compound, KHCO3. This mass here, the 39, this is the molar mass of potassium. So when we find the percent, what we're looking for here is the molar mass of potassium divided by the total mass. Okay, so let's go ahead and figure out the molar mass, and then we'll plug into this equation here on the far left. So the molar mass that we calculate is 100 grams per mole for the entire thing. So what we're going to do here is take the mass of potassium. The mass of potassium is 39. We're going to divide that by 100. And then we're going to take this and multiply this by 100, and that'll give us the percent. So in this particular case, when we do that, we take 39 divided by 100. The hundreds cancel each other out, and so the percent potassium is going to be equal to 39%. There's your answer.